All right, so this is 1-1. You can see I'm already recording. We are going to be looking today, this is all warm-up stuff. This is stuff you ought to probably already know. So what are we doing today? We are going to describe subsets of numbers. Not just numbers, but the real numbers. Okay? And we are going to identify and evaluate functions. Woo! I don't know what that is, but whatever that is, it's bad. Guys, honestly, I don't know. Plumbing? Something back there's possessed. Okay. We'll come back to the other ones if we get that far. 3 and 4 have to do with section 1-2, and I have a feeling we'll get through 1-1. We may not get all the way through 1-2. So we'll come back to that first page in these second two sets in a minute. All right, function basics. You should know the real numbers and their subsets. All right, real numbers and subsets. Real numbers are separated into real, and actually this overall is complex, by the way. These are the complex numbers, real and imaginary. Okay, imaginary, of course, is anything to do with I, which would be the square root of -1, right? So anything that has a negative square root is an imaginary number. The reals are the rest of it. Within the real numbers, you have the irrationals. Irrationals and the rationals. Okay? The irrationals are known as I. Rationals are Q. Okay? These are all capital letters. Now, what makes a number irrational?
If it's like ongoing.
Yeah, if it is a repeating, non-terminating, non-repeating square root number, okay? Usually it's the square root of something that doesn't have an even square root, like the square root of 3, for example. Non-repeating, non-terminating numbers. Now, if it's repeating or terminating, it's irrational. Rational numbers are what we consider P over Q. And I do write them as P over Q because we will come back to that when we talk about rational functions and roots of rational functions. In other words, they can be written as a fraction, right? Okay, so rational numbers can be written as a fraction. A subset of the rational numbers, subset meaning we're going to get smaller as part of the rational numbers. We get to the next smaller one, which is the integers. That is Z. Integers. Anybody give me an example of some integers? -6. +3. 0. 124. In other words, they're all the tick marks on the number line, aren't they? That's how I usually tell people to remember it. They're not the in-between spaces. They're just all of the positive and negative whole numbers, right? And 0. Okay, so like -2, -1, 0, 1, 2, and so on in both directions, okay? Those are your integers. Inside the integers, we break it down again. We have a subset of the integers, which is the whole numbers. Whole numbers is, wait for it, I know this is going to be shocker to you, W for whole numbers. Reals, by the way, is R. Okay? Whole numbers would just be 0 forward. Yep, 0, 1, 2, and forward. To go from the whole numbers to the integers, we just add the negatives in, don't we? And then finally, we have one more subset. The natural numbers. And guess what the natural numbers are?
Everything
The counting numbers, yes. Everything except 0. If you think about it, 0 is not really natural. And the reason I say that is because we came up with numbers because the caveman somewhere went around and said, Og has 1 of these, 2 of these, 3 of these, 4 of these. You could literally count. You've got fingers, right? Okay. 0 can't really be represented that way, can it? Do you count something if you have none of them? No. So natural is the natural. It's natural to count things that you have. 0 was it was like the first major math discovery, if you think about it. Aside from adding and subtracting, the idea of having nothing and recording it as a number was a major step in mathematical development. So naturals are just 1, 2, and so on.
Is that in?
Hmm?
Is there a letter for natural?
Yeah. Guess what it is? And it's always the first letter unless that's already been used. So for like integers, I was already used for irrationals, so we had to go with something else. And guess why we picked Z? Say the word.
Integers.
Z. Integers. So Z. Reals is R. Rationals, I can't tell you why they picked Q. No idea. R was already taken with real, so they had to pick something else. So they picked Q. So be it. All right, so those you need to know. All right, so if we have those, why do we need to know these? Well, we need to know those because we need to know how to write them and use it, what type of set something's part of, and then how to write using set builder notation. All right, so what is set builder notation? There are 2 types of notation we're going to use here, interval and set builder notation. Set builder notation goes as follows. All right, it tells you the set of numbers it's part of, okay? In other words, we use the properties of the numbers to describe the set. I'm going to change colors because red makes it look like I'm mad at y'all, and I'm not. There's no angry math. So what does it look like? Bracket. You're going to use the variable. In this particular case, if we're talking about domain, what letter would we use? Nope. X. X. Such that. This line means such that. So we've defined the variable, and now we're going to define what the variable is in terms of the numbers, okay? Such that X is greater than 3, where X is an element of, and you're going to say what set it's an element of. Let's say X is an element of the integers. So from that, I could make a list of all the numbers that satisfied that condition. What would my numbers be? What are the integers, basically, that are greater than 3?
4, 5, 6, 7.
And so on. So we could literally write the set of numbers. This would be 4, 5, 6, and so on, wouldn't it? But do you see how that describes? This is the set builder notation right here. You define the variable, you put a line, that line means such that, you define what the interval is, and then you tell which set of numbers, because this would be a different answer if I put X was a real number. Or if X was only irrational numbers. Then I'd have to find all the irrational numbers bigger than 3, wouldn't I? So it would be different depending on which set you're dealing with. So let's look at A and see if we could actually write this as a set builder notation. We're going to use X. So we're going to do this. X such that X is what?
Greater than 7.
Well, we could either do greater than 7 or we could do what? Greater than or equal to 8, probably safer. Where X is an element of what? This is where you want to be the least inclusive. So what is the smallest set that X, 8, 9, 10, 11, and so on are part of?
Natural.
So X is an element of the naturals. N. Yep. See how easy that is? It's not too bad, is it? How about X less than 7? Did you see how that in A, there were enough numbers that we could tell what set it was part of, couldn't we? Can you tell what set x less than 7 is a part of? Then we have to go to the most inclusive. What's the most inclusive set? Nope.
Oh, rationals.
Reals. Reals is the most inclusive. So is there anything to make it more exclusive than reals? No. So we have to go with reals. So how do I write this? X such that what?
X is
Yep.
less than 7.
Yep. Where X is an element of the
Real numbers.
R. Real numbers. Yes. Now, all multiples of pi is tougher. This is a special type of, we can do pi if we want to. You're more used to seeing that. Is there anything that, see, you want to think irrational, but here's the thing. Multiples, this word multiples is the problem. Because we know it's going to be something pi. What would multiples of pi be? 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, negative 2 pi, negative 3 pi, negative 4 pi.
Imagine.
What are those numbers? Integers. So it's going to be the set of integers, but what are we really describing? The pi stays the same, doesn't it? What are we describing as an integer? The number that's in front of it, aren't we? So think about it that way. So we're going to do x such that x is equal to pi n. Do you know why I did pi n?
I and then the number.
Yeah, it'd be like, the n would be like the 0, the 1, the 2, the 3, wouldn't it? You could do n pi if you like it that way better. Where what is an element of the integers?
Where n.
Yes, where n is an element of the integers. This is a special case. Anytime you see something that says a multiple of something else, you're going to describe it this way. If I wanted to do multiples of 6, I would do 6n, and then n would be an element of the integers. Make sense to everybody? Let's try one on your own. Let me see if I've got one on here. You one at the bottom here. So why don't you guys try this one? See if you can put that in set builder notation. All right. We do our scroll brackets, right? That's what those are called, by the way. It's not a sideways bird. Scroll brackets. What do I put next? Such that.
X is less than or greater than
Okay. X is an element of what?
R.
Why does it have to be R?
Because there's nothing that can make it more.
Yeah, because there's nothing to make it more inclusive, right?
So what is really rational?
Rationals are, I'll give you an example. What if I wanted to do multiples of 2/3?
So rationals can be fractions.
Rationals are defined. That's why we said rationals. That's why up at the top we said rationals would be your p over q. Now the whole numbers are also rationals, but if we have to have something that tells us that it's just the fractions, okay? Rationals are the numbers that sort of fill in. They're all of the things you see below it. In other words, every integer, whole number, and natural number is also a rational number, but also all the spaces between those. So all the numbers between -2 and -1 are also rational numbers, but that also includes irrational numbers because some of those spaces are irrationals. So Is there a number less than or equal to -3 that could be an irrational number? There is, isn't there? So not just like negative, let's see, -6/2. That would be less than or equal to -3.
She said irrational has to be a square root.
No. Irrationals would be like the square root of something. But take the square root. Basically, an irrational has to be non-repeating, non-terminating. Now, what do I mean by that? Take your calculator and take the square root of -3, or take the square root of 3 and look at it on your calculator. You get a big long number, don't you?
Is it pi is irrational?
Pi is irrational. So anything that's non-repeating or non-terminating, like the square root. So you can write the square root of 3.
It repeat like itself.
It's not going to repeat. If you keep on going far enough, it's not going to repeat itself. It looks like it might on your calculator, but I guarantee you it's non-repeating. Repeating would be like 3.121212121212. You know, that 1-2 pattern keeps on going. So, but the most inclusive set is the reals. Okay? Really, it's the complex, but the reals are what we kind of go with. All right, so now let's learn your own. If not, I'll give you one. Nope. At interval notation. What is interval notation? Y'all have done these before. Uses inequalities to describe a subset. Yes.
I have a question about the rationals and irrationals.
Uh-huh.
So, rationals, you could put them in a fraction.
Mm-hmm.
So, is it 1/3 repeating though if you put it into decimal?
Yeah, but it still can be written as 1/3.
Oh,
That's why they're that's why irrationals are non-repeating. Yeah. So we use inequalities to describe the subset. So what are the inequalities we can have? We could have x is greater than or equal to a, but less than or equal to b. That would look like this. Bracket a, comma b, bracket. These are bounded intervals. By bounded, we mean they're equal to, okay? Or not equal to. They have a beginning and an end, right? Bounded means they have a beginning and an end. Unbounded means what? One end is going to go towards what? Infinity or negative infinity. That's what unbounded means. It means one of the ends of it's going to go toward infinity or negative infinity. So what are all the combinations of bounded intervals we have? We could have that, couldn't we? What's the difference between that and the other one? Yep. So we use parentheses for not equal to and brackets for equal to. See the difference? And then the other two are going to be combinations of, aren't they? We could have greater than or equal to, but less than, or we could have greater than or less than or equal to. Remember, we read from the inside out, don't we? So what combo is this third one going to look like? Yeah. And then the last one's going to be? You got it. So why don't you try A and write A in interval notation? Parentheses, -8, 16, bracket. You get it? All right. So unbounded intervals means something's going to go to either positive or negative infinity, aren't they? That means x could be greater than or equal to a, or x could just be greater than a. What are the next two going to be?
less than or equal.
Yep. I'm big on patterns. Math is big on patterns. If you start looking for patterns in math, a lot of times you'll be easy to remember stuff because the patterns tell you. All right, so what is the interval notation going to look like for this first one? X greater than or equal to A? Yep, infinity. Infinity always gets what? Parentheses, because you can't ever reach it, can you? And infinity and negative infinity are automatically going to be parentheses. So you can guess what the next one's going to be. Yep. Now what about the other ones? X less than or equal to A. Yep. Right?
So then you put the infinity first?
Yep. Remember, we always read, in interval notation, we're always reading from left to right. So which one comes first? Negative infinity comes first before the number does. So then you can tell this one's going to be negative infinity to A parentheses here. Okay? So why don't you take a second and do B and C also down here. Make sure you know how to do this. Oh, how do we do OR? Anybody remember how we do OR? You don't put OR in between. OR is a union. OR is a union, and we put a union symbol in between them. U for union. So we do the first one. Less than or equal to negative 16 would be from negative infinity to negative 16, bracket, and then we put the U for union. And then we say it starts again at 5 and goes to infinity. Yep. All right. So is everybody good with, you need to be able to go back and forth between the two types too. In other words, it's pretty easy to go from set notation to interval notation because the inequality is going to be there, isn't it? From interval notation to set notation is a little tougher because you're going to have to put it into an interval and then take the interval or into an inequality and then use the inequality in your set notation. Does that make sense? Okay, so let's move on to functions. You should know what a function is. What's a relation? Everybody always messes up relations. What is a relation? So everybody always wants to tell me it's a set of numbers. You're not wrong, but you're not completely right either. How do we get the numbers? What do we do typically to get an X and a Y? How do we get the Y?
You have to find it.
How?
You have to plug in the eggs.
Oh, into what?
Equation.
Oh, a rule. The equation is a rule, guys. That's what a relation is. A relation is a rule that relates two quantities. An equation being a relation that relates X and Y, isn't it? So that's how we define a relation. It's a rule that relates two quantities. I don't always say it's how we do X and Y because it could be R and T, or it could be any two variables, couldn't it? Okay? What makes a relation a function? What's the rule for something to actually be a function?
It can't have the same.
Yeah, it can't have the same X. Every X has exactly what? One X has one Y. Now, can two different X's have the same Y? Yeah, but one X cannot have two Y's. So what we write, a function is every X has exactly one Y, right? That makes a function. Or it could be every A has exactly one B. You see what I'm saying though? That's how they relate. All right, so we've got two sets. We've got an X and a Y. What is the domain?
X.
The domain is your domain are your X's, correct? And your range is your Y's, okay? I'd like to say the domain are your inputs. These are your X's, right? And your range is your outputs. Those are your Y's, okay? Now, how does the vertical line test work?
You got your pencil can't cross like if you have like
It
a
tells
circle.
whether or not it's a function, right?
Mhm.
Okay, so if we drop a vertical line through the graph of anything, an equation,
Can't touch the line.
it's not necessarily a
It can't
function.
go through the same
Yeah.
place twice.
It can't go through that function, that equation twice, that graph twice, okay? I'm not calling it a function. I'm being very careful not to call it a function because it's only a function if the equation passes the vertical line test, okay? So the vertical line test is just a visual way to tell whether or not something is a function.
Like a circle's not.
Yeah, circle is not. This also is not. If we had this, and this always messes people up.
It passes the middle.
That is not, those 4 points do not make a function. Do you know why? If we were to drop a vertical line right here, what do we notice?
It's going through 2 points.
Yep. This is not a function. Okay? However, if we did this, guess what? That's an open circle on there, isn't there? This, however, if you drop the vertical line right here, does it cross more than one place? No. It hits here, but right here is an open circle. So technically it doesn't touch it at that point, does it? So guess what?
So if it's an open circle,
Yep.
it doesn't count.
If this is open, it doesn't count. So this would be yes, it is a function. So you've got to be careful when you're looking at these things, whether or not if you've got a gap somewhere that you don't have another point, or if it's an open circle versus a closed circle. Because while this is, if I were to color that circle in, guess what? It wouldn't be a function, because then it would fail the vertical line test, wouldn't it? So that's all we do for the vertical line test. Function, not a function. All right, so let's look at some. In this class, you better get used to word problems too, because every time you have homework, you're going to have some word problems with it, and there's no getting around it. That's one of the ways we get better on the ACT and get better as math students, is interpretation. Anybody can plug and chug numbers. We want you to actually be mathematicians, right? Okay. The input value is the student's ID number. The output value is the student's score on a physics exam. So you have to ask yourself, is this a function? In other words, do you know how you figure this out? Is every single X unique?
Yes.
How do we know they're unique?
It's that individual
It's
student.
that individual student number. Is anybody going to have anybody else's student number?
No.
Now, so individual different students, could they have the same score?
Yes.
Yes.
But would that still be a function?
Yes.
Okay, so you'd ask yourself, if all of these are different, but they all got a 93, would that still be a function? Yes. So if all the X's are unique, then my answer is yes, it's a function. So do you see how you can kind of think and explain your way through this? How you decide? I can represent it with numbers, can't I? All right, any questions so far? All right, so let's look at some more. Let's look at this guy. Oops, hold on. Hang on, guys. Sorry, already got that one. Let's try a different one. Let's see. Sorry. This is why we use pencil, right? Function, not function.
Function.
Okay. What is the only thing we need to look at?
The X.
Are all the X's unique?
Yes.
So it's a yes. These are all different. Okay, look at C.
No.
No? Why?
Because it passes the same points twice.
Yep. Fails the vertical line test. Fails the vertical line test, so no. All right, let's look at D. We got to look at D. What type of shape has that equation? A parabola. Is that parabola opening up or down? Is it a parabola? It is not a parabola. It's y squared. We got to solve it for y. Y squared equals what? So y equals the square root of, but we took the square root, so we have to put what in front of it? Plus or minus. Is that a function? So for every 1x I put in,
How do you tell based off of that?
you could graph it.
So what would you type in? The square root of 2x plus 5?
You'd have to put both pieces in. On the first one, you do y sub 1 as the square root of 2x plus 5, and then as y sub 2, guess what you'd have to put in? Negative square root of 2x plus 5. So you'd have to put both functions on at the same time in your equation editor. Where's what? Okay.
It says invalid.
Where do I put my graph?
What does it say now?
Let me see what it says. Invalid for what reason?
It said invalid dimensions.
Yeah, it means that your window's not right. Here, let's look.
It cross is not applying.
Uh-huh. All right, so you just have to look at what your table is set for, or
It's
your
supposed to be 10,
format.
10.
Oh, you got a stat plot on, that's why.
I'm just- Wait, is they teaching this? Yeah, he teaches dual. I heard it's easy.
Okay. So you tell me.
No.
You can look at the graph and see that it does not follow what? Does not pass the vertical line test. Okay. So this is no, it fails the vertical line test, right? All right, so look at E.
No. Because it has fobs.
Good. So that's a no. And look at F.
Yes.
Good. It passes the vertical line test, doesn't it? All right.
What about G?
Do we have a G? Oh, there's G. Okay, so solve it for Y.
Divide by
2x plus 6. No.
3. We gotta divide by
You gotta
3.
Mm-hmm. What is that graph as? What would that graph as? You don't need to put it on your calculator. What would it graph as? Y equals what? A line.
So yeah.
Diagonal line.
How do you know?
Tell me. I don't even care exactly what it looks like. I just need to know it's a line
Yes.
that's not vertical.
How'd you know that was just gonna be a line?
Because it's
Y equals mx plus b.
Oh.
It's just.
Yeah, I knew that.
So is it going to pass the vertical line test? Yes. So is it a function? Yeah. It's a line. So sometimes you can just look at the equation and see. All right, so function notation. What is function notation? F of, so y equals negative 6x would in function notation be f of x equals negative 6x. This is how we name functions. We can't call everything y sub 1 and y sub 2 and y sub 3. So instead in math, we name them f, g, h, j, k of x. The of x means the variable that is the input. Okay? So if I wanted to find f of 3, it tells me to plug 3 into the function f, doesn't it? So you have g of x equals x squared plus 8x minus 24. It says find the function value. Let's do the first one and see. So what are we going to do? Plug in what? Okay.
Yeah, I got 60.
36 plus 48 minus 24 is indeed 60. So g of 6 is 60. What about negative 4x? What are we going to do? Plug it in.
Please excuse this interruption. When the bell rings at 1:28, the only students that are to leave class are the students that have 4th block CAD or 4th block co-op. All other students are to remain in 3rd block.
Do I have any
Have a good
CADs or
afternoon.
co-ops? Couple? That's fine. No. Sports are not allowed to leave. Not without explicit, anybody else, you have to have permission from Mr. Garth. I have to get an email from Mr. Garth. So what is negative 4x squared?
16x squared.
Yep. And then what?
Plus 30.
Minus.
I meant negative x squared.
Okay.
That's all it, that's it.
What's negative 4 squared? If it's in parentheses, everything in those parentheses gets squared, don't they?
So we leave, that's the answer.
Can you add any of that together?
Wait. Okay, on B,
Uh-huh.
8 is supposed to be 8x, so wouldn't that be,
Well, you replace x with what?
4x.
Negative 4x.
oh, okay.
And it's multiplication.
That just threw me off.
And so you just leave it like that, because you can't do anything else.
That's right. Those terms are no longer alike. All right. G of 5c plus 4. Now this becomes fun.
Distribution.
5c plus 4 what? Squared plus 8 times
5c plus 4.
minus 24. Do y'all know how to do this fast in your head? This 5c plus 4 squared? You're going to square the first term. If we square the first term, what do we get? 25c squared. And then you're going to multiply those together and double them. What do you get? Multiply them together, you get what? 20c. Double that, you get what?
Is it like,
So it'd
So
be
you
plus.
multiply the 5 and the 4.
Yep. And then you square the last term. I call it square, double square.
Cause then, and then you, yeah.
So plus 16. Now we can do distributive. Do y'all see? I squared it, I did this and doubled it, and then I squared that.
Okay,
Squared, double square.
Oh, so you still squared the 4.
Well, yeah.
So you done 5
Look.
plus 4 and got 20 and double.
Think about it. 5c plus 4 quantity squared is the same as 5c plus 4 times.
Okay, where did the 16 come from?
it's like that thing Coach Pierce said, something with the 2 and
Oh, never mind. Okay.
Then you drop
Foil
the
it.
zeros. Foil, yeah, that's what he was talking about.
Right? But the inner outer is the double. Think about it. This gave me this. Inner, outer is exactly the same, so it gave me, I just doubled. And then last gave me the 16. Now,
It would be 40c,
plus 40c plus what?
32,
Minus,
24.
and then you just clean it up, okay? All right, before you leave, you have homework to do. We did not quite finish implied and excluded values, but I want you to do everything on 1-1. Practice 1-1, right? If you look at practice 1-1, let me see it real quick. All the way through 11. So do 1-1 through 11. On the front side, do through 11. And then on the back side, do 1, 2, and 3. 1 through 11 and 1, 2, and 3 on the back side. So 1.1, 1 through 11, and then on the word, do 1 through 3. And if you are CAD or co-op, you can go. Yes, you may, but I need you to fill out the pass because otherwise you'll get in trouble for being in the hall. Fill it out and I'll sign it. Now, if you're staying in here, I highly suggest you use this time every day to do your homework. That way you don't have any, right?
Are we still not allowed to pick out our phones?
Co-op, you can take a, not co-op,
Yes, sorry. Wait, you caught me with a mouthful of liquid. You may have your phones out during
So don't we
AHOP.
search the sign out sheet?
For the restroom. Over on that, as you come in the door, you'll see it.
So number 1,
Yep,
we solved it like how we did example 1A.
probably, yeah. Yes.
like, do we have to ask?
Just sign out. And as long as it's not like, 42 of you going at the same time. There you go.
This class.
They all do on the